Hey, well, I can see it and you can see it. I don't know. I don't know what's happening. I don't know what kind of weird possession happened here, but it's okay because it's Pi Day. March 14th. Yeah, March 14th. So I am recording, I think. Yes, this is good. All right. So we're going to start talking about compound interest. This is what I wanted to do last week, but the snow day and the weird schedule, I don't know, it just kind of got in the way. So this will take a while. We got to make sure you guys understand how compound interest works before we can appreciate what's going on here. So the simplest example that we would always explain this with is, let's say you invest $100. Let's do $1,000. Why not? So I don't know if you've ever talked about this. I know that Mr. Spatz used to do it out there in the ag shop quite a bit. So I don't know who's seen it or who hasn't seen it. But the way compound interest works is you make interest, it goes into your account, and then you make interest off of that interest. It compounds on itself. So let's just do a nice simple example. Let's do annual interest. And of course, you know what that means. And so let's keep it simple at 10%. And so the way it works is you go and you write a check and you give them $1,000. And at the end of 1 year, how much do you make in interest? Say again? $100. 10% is a tenth. A tenth of 1,000 is obviously 100. So you, after 1 year, you add $100 in interest, and you're now sitting at $1,100. Do you agree? And so then that money just sits there, and at the end of the second year, how much interest do you get? You get $110. That's obviously 10% of your new balance. And so now how much money are you sitting at? Thank you. $1,210. And how much interest do you then get at the end of the next year? $121. So we add $121, and our new balance is what? $1,331. How much interest do you get at the end of that year? You get $133.10. All right, we're not going to skimp or round here. We want to be accurate. How much would we have at the end of that year? Careful, I've not lined up my decimal points very carefully, so I need you to not make any silly errors here. I'll try to scoot it over a little bit here. There's that better? So $1,464.10. And so this continues, right? And you can imagine that we wouldn't want to do this for like 50 years. And it can get even more complex than this. Let's just say, so I get my interest rate, my annual interest rate of 10%, but now let's say that the interest compounds quarterly. Do you guys know what quarterly means? Quit your yip yapping, okay? We got to do this. So quit your. It means it happens every 3 months. It literally happens quarterly. So once every quarter of a year, which means that at the end of 3 months, you get 2.5%. At the end of the next 3 months, you get 2.5%. So you're still getting your 10% interest, but if it's quarterly, then you're getting 2.5% in the first quarter, 2.5% in the second quarter, 2.5% in the third quarter, and 2.5% in the fourth quarter. So you still get 10%, but what happens is you get it in smaller pieces, but more frequently. Do you think that affects how much interest you make over the course of the year? It does. Quite substantially, it does. And so the more frequently your interest compounds, then the more in the end you wind up making. And I said significantly or substantially, and perhaps that was hyperbolic. I mean, it's not that big a deal, but it's kind of a big deal, like it matters. And so we arrive at a point where we certainly don't want to keep doing these by hand, right? Like that was not even really that exciting. And we just did it for like 6 years or 5 years or something. Now imagine doing it for 40 years compounded daily. So that would mean that you have to take your 10% interest and divide it into 365 little pieces and get that much every day. Now imagine again doing that for 40 years. That would take all day. If you were lucky, you'd get it right. You know, you'd probably I'd probably hit a wrong button on a calculator and go, oh my God, I got to figure out where I went wrong. So as you know, I'm sure where this is headed, there's a formula for this. But you have to understand kind of behind the scenes that that's what's happening. Is you're getting a little piece of your interest, it fuels, it injects it in, you get a little more, it injects it in, you get a little more. And over time, you obviously get like a final value, we say. Okay. So having said that, having given you that little introduction, I hope that the following formula is appreciated by you, and you're going to come to know this fellow oh so well. This will be your best buddy for like the next 3 or 4 days. So here's the formula for compounding interest. It's one of 2 formulas. It looks like this. If you don't write that in your best handwriting, go back later when you realize how important it is and rewrite it in your best handwriting, and then put a big like highlighter box around it, because like I said, you'll use it all the time. So capital A equals capital P, and then in parentheses 1 plus the division problem, R divided by N, and then all of that raised to the power of N times T. Now, a formula is only worth any good if you know how to use it, if you know what all the stuff stands for. So let's go through the cast of characters here, and let's talk first about A. And A is, we're going to call that like your final amount. And I say final, and I don't know if that maybe is the right word, but it means like at a certain point in the future, if I want to know like how much money is in my account after 30 years, then that amount of money is going to be represented by A. A is like your ending sort of value, if you will. You want to guess what P stands for? Yeah, it actually stands for, I'm sure someone said something funny. Thanks for that. P stands for, what'd you say, poop? Some pancakes. Nice. Well done, guys. Good job. Good thinking. Good forward thinking there. So P stands for a word in math in the world that we call principal. And the principal value of an investment is how much you start with. So again, if you inherit some money from a grandmother, grandfather, whoever, and you go and you write a check to like, I don't know, who's like a big Dane Rauscher or something, I don't know what they are, like the big Charles Schwab. You go and you give them money and say, I want you to invest this. That amount in that check that you start with is called the principal value. And so you're welcome to just call that like starting value or starting amount, I guess, to be consistent. The number 1 is obviously not a variable, so we don't need to talk about that. The 1 is there to ensure that we don't lose money. So the entire 1 plus, bless you, thing says that, all right, I got 1, I'm not losing any money. So when I multiply my principal by 1, that's my base. And then the plus R over N, that's where the interest takes place. So let's talk about these guys. R will come next. You guys want to guess what R stands for? Say it again. Rate. Very good. If you're taking good notes, make sure you put a little comment to yourself that the rate needs to be input as a decimal value, right? And I'm amazed always in a high school class how often that's the source of errors. I see like if I put 6%, you'd be amazed how many 17-year-olds put 0.6. It's absolutely ridiculous. What is 6% as a decimal? 0.06, right? I mean, good Lord Almighty. So make sure you take your rate and move the decimal 2 places to the left, always 2 places. There are no exceptions to that. 2 places to the left, and that's what will go in place of R. N, anyone want to take a stab at that? Nope. Very good. It's the number of times per year. I mean, these variables aren't that obscure. A stands for amount, P is principal, R is rate, N is number of times. And of course, you would logically at this point guess what T stands for. What's T? Time. And that is in years. Notice I didn't redefine N in the exponent because, well, we already know who that little joker is. So he will appear twice in your formula. He appears once as the divisor of your interest rate, and then he appears again as the multiplier of your time, which will all make perfect sense when we get right down to it. Okay? So, got the formula? Might want to start writing this down. They got it? No, I'm not a financial advisor, but I mean, I could tell you, like, if you get like 8% return on money, that's pretty splendid. Yeah. And again, don't be confused either. Like if you just go open up a bank account, like at Pinnacle Bank, and you don't get this kind of interest. Okay. So when we talk about these, we're talking more about investments. Like, you guys ever heard of like a mutual fund, or when people talk about their portfolios? And so that basically is, you trust people who do this for a living and they play with your money. They make a lot of money off of your money, and then you get a return on that. So you get a certain portion of the return, and there are no guarantees, obviously. But generally you can find like over, you don't want to base anything on, here's what this fund has done over the last 5 years. You want to look at, talk to someone who knows what they're doing, and they'll project, this is what this fund has done over the last 20 years and what we project it to do over the next 20 years. Like these are, you ever seen the stock market thing and how it looks like a roller coaster going up and down? And so you hear people talk all the time, like, don't panic. Like, if something happens, just ride it out, ride the storm. Because if you go from point A to point B, there might be a lot of zigs and zags in between there where people go, oh my God, I lost $16,000 today. But then you ride it out for another 6 months or 2 or 3 years, and eventually that roller coaster generally comes back up. So we talk about generally the growth from point A to point B, which might be 20 or 30 years down the line. And there's a lot of action that happens in between there. Got it? So anyhow, let's talk about the cast of characters here. And there are generally going to be a ton of variables in play, right? So can you tell me what 5,000 represents? Which variable? P. Very good. And so I think while we're getting really kind of started on this, we want to take time to say, okay, as I read this word problem, I want to figure out what each thing stands for. And 5,000 is what I invest. Therefore, P is 5,000. And you don't need to put dollar signs or anything like that. Okay, what's R? Say it again. No. 0.084. Okay. I can tell you over the next 2 weeks, there will be in this class alone, probably 70 or 80 points lost on decimal issues. You have to decide right now if you want yourself to be in that clan or if you want to just let it be somebody else. Do not forget that your interest rates have to move the decimal 2 places to the left, right? They are always decimal values. Let's see, what else? What is N in this problem? Very good. N is 1, and that comes from this word annually. Annually means something happens 1 time per year. And then, of course, T is 45. Very good. You'd be wise, I think, to go in and like set this up and actually write out your variables. Notice the only one that we haven't listed is A, right? Because when I read this problem, I understand that A is what I'm trying to calculate. There's not going to be a whole lot of algebra with this one. This is our warm-up problem. This one, basically, all of the work will happen on the right side of the equal sign. We just type it in our calculator, let it do the heavy lifting, hit enter, done, easy. So let's do this. Let's set this thing up. So what it's going to look like is A equals, what are we going to put in place of P? So we have 5,000, and then we open a set of parentheses and always put 1 plus. And what is R? Nice. And what is N? 1 to the power of 45. And for the sake of making proper notes, I'm going to put 1 times 45. Now, you'll notice in a case like this that there are a couple of numbers in this particular instance that don't need to be there. You come to realize when it says compounded annually that the formula actually simplifies itself quite a bit. Like, what's the point of doing 0.084 divided by 1? Well, there really isn't one. And so instead, in this case, I elect to make my life easier and just write 0.084. Generally, you won't get away with that. You got to put like over 2 if it's semi-annually, or over 12 if it's monthly, or something like that. And then again, like Dylan, I think, said, the exponent doesn't have to be 1 times 45, although that is N times T. I could simplify my calculator input by just, in this case, putting 45. Got it? So if we did this by hand, understand that we would have to do 45 iterations of that process that we started class with. We'd have to take our $5,000 and we'd have to multiply it by 0.084, add that in, and then take that new number times 0.084 and add that in. And you get really, really sick of it after, like, I don't know, 3. And you go, oh, I only got 42 to go. And so this formula is going to just expedite the whole process for us. So as has been the case for weeks now, if you don't have your calculator, you're going to miss out on being able literally to do anything. You're just crippled. You can't keep, this work is all calculator. So let's all type this in. See if we can come to an agreement. Yes. I hope you guys, I have a mission for the next week. Number 1, I want you to learn how to do this. Number 2, I want you guys to appreciate that sometimes in life there are cliches. There are things that grown-ups say that kids are just like, shrug, whatever. But here's one that I hope you take with you. If you start investing when you're 20, the amount of money you have when you're 60 is unspeakably larger than your friend who waited to start investing until they were 30. And the reason is because with compound interest, as you can see from that number, it grows. It doesn't grow a lot in the first 10 years, even the first 20 years, because the curve is pretty much the way an exponential curve looks is it starts out kind of like, meh, okay, look at me, how exciting, how exciting. And then you hit, every exponential curve has like a breaking point where suddenly it just goes wham. And that's where you want to get to, is here. If you start investing when you're 40, then that exciting part of the curve doesn't happen until you're 75. By that point, well, you know, you're 75, right? So that's why anything you can, sorry, don't want to hear my parents hear me say that because they're pretty old. But anyways, you want that exciting part of the curve. You want that exponential action to take place while you're 55 or 60, right? And that's the benefit of investing early. So you guys all should have gotten $188,489.73. Does that sound correct? I will show you how to do that, yes. So the way I typed that into my calculator is I typed in 5,000, and then I opened a parenthesis. You have to do that yourself. And then I typed in 1 plus 0.084, and then I closed the parentheses, bless you. And then I went and I found my exponent button. Every calculator manufactured in the last 50 years has one. And then after the exponent button, I hit 45. And then I hit enter. And again, your answer should be, when you're done, 188,489.73. Any questions about where your exponent button is? On the TI-30s, it looks like a little up arrow. It's like a caret on a keyboard. What model do you have back there, Shelber? Yes. Yes. Is that an old TI-30? It's a TI-30. Yeah, that's going to be let me look at that in a bit. Yeah. If it's not the X2S, it's going to be, it's not infinitely more difficult. It's just a little bit more annoying. And I'll look at it. I just want to keep rolling, okay? Okay. Did those of us that found our exponent buttons, were we able to come to consensus? Good. Say again. I'm going to pause this real quick while we have calculator shenanigans going on. So I hope you were able to find success with that. If you want to practice again, do the exact same calculation, but let's take a look at it for 55 years. So do the same calculation again, 5,000, parentheses 1 plus 0.084, close parentheses, to the power of 55. Should we start investing before you're 18? It's a good question. And then when you turn 18, you can. So if you did this correctly, after 55 years, you should see that your amount of money has jumped by up to almost $500,000. So $422,260.57 after 55 years. So just adding 10 more years. I know 10 years to you guys sounds like an eternity, but if you can think about getting to that point in your money's growth, that's why if you can invest young, then you have more wiggle room on the end as to when do I want to dip into this. And those 10 more years are going to buy you another $240,000, which is pretty significant. You're welcome to play with this formula all you want, and you're welcome. Obviously, you're going to get to over the next few days, but you'll see. All right, there are things you can do. Obviously, investing more is a no-brainer if you can. Investing periodically, putting money in helps a lot, and we would have to tweak the formula for that. A higher interest rate is obviously better. More frequent compounding, as you'll see, is even better than that. Some people invest like that is, you hear that a lot, and people do literally live off their interest, yes, but that's not to be taken lightly. I can assure you that most of us are not quite that fortunate, I guess. Let's do the same problem now. And what I want to do is I want to go back, and I don't want you necessarily to write this whole problem over again, but I do want to see if I can get in here and edit this. And instead of annually, let's change this to monthly. So that's going to change what we do, right? And so like, again, I don't want you to have to rewrite the whole problem. I don't know how you want to do this in your notes, but just kind of make a note somewhere that, okay, we're doing the exact same problem over again, same initial startup money, same annual interest rate, same 45 years, but rather than the money compounding just once at the end of the year, we're going to have it compound once at the end of each month. We're still getting 8.4% per year. But that 8.4% is divvied up over the course of 12 different little pieces. And that's what the formula takes care of that for us. And so the only thing I would have to modify is here where we have n equals 1, for our next example, we would need to change n into 12. Okay, everybody got that? So I'm going to do a little bit of erasing up here on the board. And we're going to redo our formula. It's still going to say A equals. It's still going to say 5,000. It's still going to have an open parentheses. It's still going to have 1 plus. It's still going to have 0.084. But now I can't poo-poo this like it's not important. What goes under the 0.84? The 12. And I hope this is kind of where it comes together, how this formula works. What's my exponent going to be? Yes, it's going to be 540. And that's the result of 12 times per year for 45 years. Again, you're still getting 8.4%. It's just happening in smaller pieces more frequently. That's, yeah, I don't know how to answer that really. I'm not sure that that's up to you. Got it? So again, it's happening 12 times as often, but each time is 1/12 as much. And again, to the inexperienced, you might say, well, it's the same thing, same. Why are we even talking about this? Well, let's practice again with our calculator. So we're going to type in 5,000, open parentheses, 1 plus 0.084 divided by 12. Close parentheses, find your exponent button, and then put in 540. And you'll see that it's not massively different. It's not like, whoa, my goodness gracious, but it will be more. I just don't necessarily know that that's up to you. So it's about $30,000 more. Is that about what you figured out? Yeah. So if we go from annually to monthly, we go all the way up to $216 or $216,000. We got 214, and then the change is 15 cents. So almost $30,000 different if you get more frequent compounding. Bless you. So far, so good? Now, think about this, and we will watch a YouTube video on this because I think we need to, not today, but we will, cross my heart. What do you think would happen if we went to daily compounding? No, I mean, like serious answers, I would appreciate. What happens to our money if we go to daily? It's going to get bigger, isn't it? Because now we're getting our 8.4%, but we're getting it 365.25 times. You got to factor in the leap year, right? Because every 4th year there's an extra day. So 365.25 would be our end value. What happens if it compounds every hour? Then it's that times 24, right? What if it compounds every minute? Times another 60. What if it compounds every second? What if it compounds every millisecond? Times 1,000. What if it compounds every nanosecond? I don't even know what that means. You reach a point where your brain starts to understand, in theory, could something compound just all the time? Could it constantly just be compounding? It can. And there's another name for that. And welcome then to the second formula for the day, and that is called continuous compounding. And that means it's literally continuously compounding upon itself. It's more frequently than once every billionth of a second. constantly compounding. It's hard for the human brain to even understand. For that, we have a new formula. And it's this one. I always call this the PERT. Call this the PERT. Been calling it the PERT formula for years and years and years, and people go, oh, I got to use the PERT. So remember, this formula is for compound continuously only. Anything else, quarterly, monthly, daily, hourly, semi-annually, whatever, you use the other formula. This one, you got to use the PERT. So let's do the exact same problem again. Might as well, right? I mean, why not have like that point of reference? So we're going to do the exact same problem again, but we're going to do it for continuous compounding. So again, the numbers don't change. The only thing we're not going to have this time, obviously, is an n. Because what would n be if it were continuously compounding? It would be this, infinity, and that ain't happening. And so when we watch a YouTube video, if you're actually interested, which I am, I always am, you'll see where the E comes into play and how you cannot just put infinity in place of N. So just remember the name Jacob Bernoulli. So anyhow, let's do the same problem. So it's going to be A equals 5,000 times E to the power of 0.084 times 45. Before you figure out how to type it in, and I may have to pause the recording again here while we screw around trying to find the E button. Before you type it in, make a conjecture. What do you think is going to happen to the answer this time? It's going to get bigger, isn't it? I mean, it's not going to blow your socks off. You're not going to go like, oh my God, $2 million. It's not like that, but it's going to be bigger yet even than the what we do, monthly? It'd be bigger than the daily, which we didn't do. All right, so let's try typing it in. I assume by now you've figured out where your E button is. I hope. Hi. Hang on a second, I gotta pause this recording. A lot of you have a button on your calculator that will look like this. Okay, if that happens, then you're already set. Just make sure that the entire thing, 0.084 times 45, goes in the exponent. That's important. You might need parentheses for that. The answer, I can tell you based on what I have here in front of me, is $219,000. $219,080.21. So I'm going to pause this real quick. As you can see, it's not that much different than the monthly, right? There was a pretty substantial jump when we went from just once a year to 12 times a year. Not that big a difference when we went from 12 times a year to infinite times per year. All right, so it's not, like I said, not going to blow your socks off, but it will. That's the best we can do, is the continuous compounding. This is how much money would be in the account after 45 years. A stands for the final amount when we're done. Got it? Now, I'm going to power through. I got about 7 minutes here. If that were the only part of the lesson, that would not be appropriate for Algebra 2. That is very, very simple, light work. The reason we teach this in Algebra 2 is because now we get the joy, the pleasure of solving for other variables other than A. A is just a matter of, do you know how to use your calculator? You just type it in, hit enter, boom, copy it on your paper, and you're done. It gets way more exciting when we have to solve for the other variables. And there are 3 of them that we will solve for, not 4. I know there are 4, but we will never, ever solve for n. And I will tell you this so that you don't ask this question like as a challenge. I am almost 49 years old. I've been doing this for almost 26 years, and I do not know how to solve for n in this formula. And I've Googled it, and I think I've talked to like 8th year math professors at universities who say solving for n is more complex than I can get my head around. Got it? So I'm owning that. I have no idea. I would never even try to go down that road. The variables that we will solve for are P, R, and T. Ready? So let's begin with a question, and I'm probably not going to have time to finish this today, but let's begin with a question where we solve for something else. So after 30 years, your account is worth $78,500. If you received 6.75%, annual interest compounded quarterly, what money did you originally invest? Notice I put 6.75% annual interest. That does not mean that you get that once a year. That's not the phraseology there. That is just called an APR. That's an annual percentage rate that can be broken down further than when we talk about the frequency of the compounding, which if you read on, you realize, oh, it's compounding quarterly. So again, the 6.75 is just how much I get over the year. Call that annual. The compounding, though, is not annually. So let's go through, as I said before, and make a cast of characters. What is $78,500? That is A. Well done. So A is going to be 78,500. Well played. Let's keep going. What is 6.75 going to turn into? R, which is? Nice job, Sam. Turn that decimal, move that decimal 2 places to the left. 0.0675. And what else do we know? T is, we don't know. Oh yeah, we do know T is 30. And then do we know anything else? No. I thought I forgot to type it, but it's right there. It's up at the top, right at the beginning. What's the other thing we know? What is N? Quarterly, but I can't put quarterly into the formula. So what's N? 4. Good. Remember, N literally stands for number of times per year. Quarterly implies 4. All right, so we're going to take, I know that some of you are pretty resistant to showing work, but I'm not going to go down that road. No way. So I'm going to show the formula out, only I'm going to put numbers in place of letters. So the formula, remember, is A equals P times 1 plus R over N to the N-th, and I'm going to put numbers in. So I'm going to have 78,500 equals P. Whoever you're looking for is going to stay as a variable, right? Always. That's how math works. And then we're going to put 1 plus, and what's going to go on top of my little fraction? Divided by, to the power of? Thank you, 120. Good. 30 years, 4 times per year, 4 times 30 is 120. Now, this time we have to actually do a little bit of algebra. So the algebra student in you says, I can do this. I can solve for P. I know how to solve an equation. If you think about it, what's really going to happen here is I just need to divide both sides by that yellow box, right? Can't disagree with that if I want to get P by itself. So how we're going to type this into our calculator is 78,500 divided by 1 plus 0.0675 divided by 4 to the power of 120. I, as a student, would be inclined to say, hey, Mr. Ahern, don't you need to put some parentheses here and here? And the answer is no. And the reason is because my calculator is smart. It knows the order of operations, and it's going to do these things in the order that I intend. The exponent will go first because someone got paid to make sure that it would. So if you want to put in those blue parentheses just as like a safety net, you're welcome to. The white parentheses up there you need. The blue ones, yeah, it's going to work. So let's practice typing it in. Anybody got an answer? What'd you get, Carter? Attaboy. In order to accrue that amount of money or have that amount of money after 30 years at that interest rate, you would had to have invested $10,538.07. Got it? 30 years. Yep. So your 10,000 would turn into 78,500, assuming you get that interest rate compounded monthly or quarterly. Yeah, anytime you hit that 30-year mark, then things are starting to look good. So this lesson, as advertised, takes a long time, and quite frankly, I'm not even done. However, that clock back there on the wall is my boss, and it's telling me that I have to shut up. So no homework tonight. Tomorrow, we're going to resume notes for 15 minutes or so, and then I'll give you an assignment. Got it? Okay.